Dear students, in my previous video, I discussed the economical operation introductory aspects. So in this video, I am going to discuss about the economic scheduling problem. The economic scheduling problem. So this economic scheduling problem means it is the distribution of load among the selected units. So this economic scheduling problem comes under three cases. In case one, the scheduling problem without losses and without limits and without losses and without constraints or limits. The second case is the economic scheduling problem without without losses and considering limits and considering. So that is the constraints are taken into consideration, considering limits or constraints. Third case is the economic scheduling problem considering losses or including losses. Considering losses or including losses. So in this video, I will discuss about the economic scheduling problem without losses and without considering any limits. So first case, therefore, for this purpose, we consider a station K, a thermal station K. So with or a thermal station with K number of generators committed for operation and the load demand is PD. So a thermal station with K number of generators committed for operation and the load demand PD is given. So here the problem is the allocation of real power generation PZ. So the PZ, the allocation of the real power generation PZ among these K number of units with the objective that the total cost of generation should be minimum. So with the total cost of generation to be minimum. So what is the total cost? Suppose I equal to 1 to K, 1 to K. So total cost equal to C1 plus C2 up to K. So sigma of I equal to 1 to K, Ci of PCI. So that is the cost function. We have to minimize the cost function with equality constraint. Always in the power system, the power balance equation has to be satisfied. So this is called the equality constraint. What is equality constraint? PZ equal to PD plus losses. But this is the first case we are considering. Therefore, what is the first case? Neglecting losses. We won't consider losses. So the objective function is the minimum cost of generation with the constraint that generation should satisfy with the load demand. To solve this problem, the economic scheduling problem, there are number of methods are there. One of the easiest method is method of Lagrangian. So when we apply this method, we can apply that the incremental fuel cost of the thermal plant equal to lambda, where lambda is called the Lagrangian multiplier. Again, I equal to 1 to K. So when we consider two thermal plants, then the economic scheduling problem, that is the solution of economic scheduling, is the incremental fuel cost of each plant should be same. The incremental fuel cost of each plant should be same. So for thermal plant 1, what is the incremental fuel cost? DC1 by DPZ1. For the second plant, DC2 by DPZ2. DC2 by DPZ2, that equal to lambda. So like that way, this is the solution for the economic scheduling problem. when the incremental fuel cost of each plant is same, then the economic scheduling can be obtained. So regarding this, we will discuss about one numerical problem. So in this problem, two plant system is considered and the incremental fuel cost of two plants are given. And you have to calculate the economic scheduling between the units when system load is 200 megawatt. That is one part. What is the other part? You have to compare this one. It's the economic scheduling when equal distribution of same load is there among the two units. Equal load sharing means P1 will become 100, P2 will become 100. So in which case the cost is less, that you have to compare. So first we'll solve the first sub-problem, that is economic schedule between the two units as the system load is 200 megawatt. So just now we discussed that when the incremental fuel cost of each plant is same, then economic scheduling can be obtained. So what is incremental fuel cost? dF1 by dP1 equal to dF2 by dP2. That is 20 plus point P1 equal to 16 plus 0.12 P2. So let it be first equation. What is the constraint given? The total load is 200 megawatt. That means generation equal to load demand. What is total generation? P1 plus P2. What is the demand given? Load demand 200 megawatt. That is second equation. That is second equation. So we substitute, we have to solve the two equation to get P1 and P2. So 0.1 P1 plus 20 equal to 0.12 into 200 minus P1 plus 16. So you will get, when you simplify, 0.22 P1 equal to 20. So our P1 equal to 20 by 0.22. So that you will get 90.9 megawatt. So then what is P2? Therefore P2 equal to total load is 200. 200 minus 90.9. So you will get some 109.1 megawatt. So when we apply economic scheduling, the P1 is 90.9 megawatt, P2 is 109.1 megawatt. What is our second part? We have to compare. So in which case the cost is less. So when load is shared equally among the two units, when load is shared equally, then what is P1 and P2? Under the second case, that is load is shared equally, P1 will become 100 megawatt, P2 will become 100 megawatt, P2 will become 100 megawatt. So in the economic scheduling, P1 is 90.9, P2 is 109.1. Whereas when load is shared equally, P1 equal to 100 megawatt and P2 equal to 100 megawatt. So now we calculate what is saving. So for that purpose, we have to know what is F1. But here what is given? Incremental fuel cost is given, that is dF1 by dP1. So how can we get F1? When we integrate dF1 by dP1 with respect to dP1, we will get F1. So F1 comparatively between the two cases. So F1 will become F1 equal to integral of dF1 by dP1 into dP1. So here you can calculate individually. In first case what is total cost, in second case what is total cost, or straight away using this integral by putting the limits, you can directly calculate what is F1 for the two cases. So here for first case, according to economic scheduling, What is P1? You got 90.19. So according to equal load sharing, what is P1? 100. P1 is 100. So this one equal to integral of 90.9, 100. So 0.1 P1 plus 20 into dP1. So what is integration of this one? 0.1 P1 square by 2 plus 20 P1. What are the limits you have to apply? 90.9 and 100 and 100. When you substitute the values, you will get 268.85 rupees per hour. Rupees per hour. So the cost of plant 1, that is F1, fuel cost equal to 268.85. So for the two cases we considered. Similarly, calculate F2. F2 equal to integral of dF2 by dP2 into dP2 with respect to P2. Now, what are the limits here? You have to write the same values. In previous case, lower limit we put the value of the value of P under economic scheduling. So in this case, second case, under economic scheduling, what is P2? You got 109.1. Here, equal load sharing 100. Equal load sharing 100. So like that you have to substitute. Lower limit, in the first case we substituted economic scheduling value. Here also same. Okay, you have to observe this change. So integral of 0.12 P2, 0.12 P2 plus 16 into with respect P2. You have to integrate. So 109.1 and 100, that equal to 0.12 P2 square by 2 plus 16 P2. What are the limits? So here what are the limits? 109.1 and 100. So you will get a sum minus 259.768 rupees per hour. So what is total cost? Total cost equal to F1 plus F2. Total cost equal to F1 plus F2. So what in first case you got 268.85 plus of minus, that is minus 259.768. How much you will get? 9.08 rupees per hour. Rupees per hour. So from the economic scheduling, so we will get the minimum cost of generation compared to load sharing equally. Compared to load sharing equally. So in next video, I will discuss about the second case.